In this video, we are going to solve the paper 4 variant 2 physics 9702 May June 2025 2 hours papers. Okay, this is structured question paper and most detailed and most important paper of your grade in Cambridge A-level exam over there. This is the latest paper which is currently given. It has total 100 marks over there. Let's move towards our question number 1. Some data insertion is given over there. If you want to use this data, it's good for you. And if you memorize these formulas, then it will be much more applicable and practicable. I will suggest that you should memorize these formulas and do practice with these formulas to implement on different question situations so that on the spot, when the time is very limited, you are not going to waste your time on searching the formula which you should use and which you should ignore over there. All right. Let's move over question number 1, where he is saying about radian. Okay, this is the question which is taken from circular motion topic over there in A levels, the first chapter over there in A2 structured questions paper over there. Define a radian. If I take a sector, if I take a complete circle over there, then the angle subtended in the center of a circle in such a way that this radius becomes equal its arc length L equal to R. That is called a radian. One radian is defined as the angle subtended at center O, like that. Angle subtended at center of circle uh, when arc length becomes equal to radius of that circle over there. That angle is called radian. And I will suggest that when I am solving these questions, you also solve the same paper on your register so that you can properly get what the concept is behind these questions over there. Let's move over next part of the question over there, where he is saying the rear wheel of the pedal of the bicycle are connected by a chain that passes around two cogs. Okay, two cogs over given, large cog and small cog. Okay, and by a chain around passes around two cogs towards two wheels over there as shown in figure. All right, and point X is shown over there. And okay, the wheel radius is 0.64 meter and small cog radius is 0.038, and this big one cog is having a 0.15 as its radius over there. Let's go what he is asking over here. The small cog, this whole data which I have just explained in the figure is written over here. Let's move this. The bicycle is being paddled so that it moves in a straight line with this velocity 17 meter per second. All right. So calculate the angular speed of the rear wheel over there. Okay. For that purpose, it means we will have to go for speed that is given V form, that is 17 meter per second, because that is straight line motion. V is for straight line motion, and here he is asking angular speed. For that, we will use the letter omega over there. And when we are going to relate our linear velocity with angular velocity, then we use the formula V is equal to R omega. And he is saying omega is equal to V over R. Remember that angular speed is always being taken by its unit radian per second or revolution per minute. But here I will use radian per second for that purpose. Speed is 17 and rear wheel is having its diameter, how much? Radius over there, and that is having 0.46 over there. So that is having 0.46, the rear wheel radius, 0.46. Let's go for it for calculation over there, where he is, yeah, okay, I'm using this calculator here. What happened with the calculator? Okay. Let's go to solve this. That is 17 divided by fraction introduced. 17 divided by 0.46 equals to this, equals to 36.95. 36.95. When I round it off, approximately equal to 37 radian per second over there. So it is 37 radian per second is already written in the form of this unit. So this is angular speed unit over there. Let's go with the here, calculate the period of rotation of the small cog over there. So period is being taken, T is equal to uh, omega is taken as, first of all, omega, the angular velocity is 2 pi over t. And from here, if I make t subject, then I say 2 pi over omega. And I am using this value over there in the form of 2 pi over omega was calculated in the previous part, which was 37 over there. Let's go to write it like as it is, 37. Let's go for solution of this. 2 pi divided by 37. So it is fraction introduced. 2 with pi divided by 37 equals to this 0.169, which is equal to 0.169, which is approximately being taken as 0.17 in the form of second as its unit. 0.17 should be taken. Show that the distance moved by point X on the chain during the one full rotation of a small cog is 0.24. So here I will use the relation about this complete way. Let's check what is the time required for this. We look on complete point of view. The point X is going here. Okay, point X is going on this point. Then he is saying here, show that the distance moved by point X on the chain during one full rotation of the small cogs. Then I will have to use the formula 2 pi r like that. And for the small cog, the radius is 0.038. And during that, what the x has traveled distance for its complete distance over there, then I will say I will use here because it is along the complete circumference. So its circumference being taken as 2 pi r, and I will take it 2 pi and r is 0.038. Let's go for its multiplication over here, which is he's saying 2 pi, 2 into pi multiply by 0.038, which is equal to 0.238. And we can also write 0.238. We can say it is approximately equal to 0.24 meters over there. Okay, that we will have to show like this. So 0.24 meter is the distance. I have calculated that distance by using the circumference formula of a circle, which was in the form of cog over there. Let's go with the use the information in B3, okay, which we have just done 0.24 to determine the angle through which the large cog rotates during one full rotation of the small cog. So that will be the arc length for big cog because its radius is long and it will take the distance in the form of arc length over there. And the radius will be also being taken, that is for big cog is 0.15 over there. Okay, then I will make here the relation that 0.15 is its radius, 0.15, and 0.24 is the arc length. And we know the formula about L is equal to R theta. Theta is equal to L over R. Then we can say L is 0.24 divided by 0.15. So 0.24 fraction introduced 0.24 divided by 0.15 equals to 8 by 5, which is equal to 1.6 over there. So this is the large cog in the angle which he was asking for, at 1.6 radian over there. Okay. In the next part, he is saying the chain of the bicycle in B is moved onto a smaller cog fixed to the rear wheel. Okay. The speed of the bicycle does not change. Explain without calculation the effect of this change on angular speed of pedal. All right. Here he is saying that the chain of bicycle is moved onto smaller cog fixed to the rear wheel. Okay, the speed of bicycle does not change. Then he is saying what will happen to the point X will be taken because that is the only point on the chain over there. So point X will move, point X will move the smaller distance over there. In the same time like that, point X will move the smaller distance over there, and at the same time like that, at the same time. And we can say here that overall linear speed of both cogs, linear speed of both cogs is going to we can say here is going to decrease, is going to decrease over there. And if I say about more about angular speed about it, definitely V is equal to R omega. As we know, V is equal to R omega. If linear speed is decreasing and radius is a constant, then it is directly proportional. Angular speed will also decrease. Angular speed of pedal will also decrease over there. All right, let's move to the next question over there. Question number 2, state what is meant by gravitational field line over there. So it is, we can say gravitational field line he is asking over there. If I define it properly, then I will say here that it is showing some direction of force over there, or it will be like force acting on test mass over there because of the uh, gravitational force or gravitational attraction of the big object over there. Then I will say here that it is a line which represents the direction of force, direction of gravitational force, gravitational force over there, and it is basically representing, or it is acting on like a test mass. It is acting on like the force. The it is the action of force on test mass over there. Okay, I think so you have got the point over there. But he want to ask gravitational field line in region when we are saying that this is the earth, and gravity is acting towards earth as all the objects are falling towards it. Then I will say here that these lines are representing, and what is this only line? This is basically the line which is representing the direction of gravity over there. So gravitational field line is a line which represents the direction of gravitational force acting on that object over there. Okay, there he is saying the earth may be considered as a uniform sphere in figure 2.1. Okay, draw the field lines to represent earth gravitational field outside the earth. Remember that here I will draw at the lines towards it. Remember that Earth is attracting all the objects towards its surface because of gravity over there. So I will say here that it will be on the Earth surface, around the surface, and always will be indicating these gravitational field lines are directed towards Earth over there. Okay, because it is attracting the objects over there. Okay, now he is saying the Earth's magnetic field may be considered as being the Earth's acting along a solenoid. All right. Here he is showing equator. Here he is showing the poles. Okay. Then he is saying in normal, like in IGCSE mathematics, when we mostly draw the north, we draw upward direction. But when we are taking in the form of solenoid, then I will tell you here, it will be geographically opposite poles over there because the earth is going to be taken as, then S will be at top, it will be reciprocal, and north will be at down. This is showing the magnetic poles present and along the poles of earth over there, then they are going to shown in opposite direction because they are geographically opposite. The magnetic poles don't align with the geographic poles, which are on the axis of rotation over there. So they remember that they exactly don't lie on the poles over there, align properly. They just show a little bit deflection also. And they are geographically opposite poles for the earth over there. Okay, here he is saying that without labels, but two magnetic field lines shown. Okay, two magnetic field lines are shown. On the figure 2.3, label the magnetic poles with the north and south pole. We have already done this. On the figure 2.3, draw the field lines to represent Earth magnetic field outside the Earth. Okay, then it means I will say here that as we know, solenoid field pattern will be at poles over there, and field lines on either side of the poles will be taken over there. And in that case, I will say here that they will be parallel to the surface above the earth over there. They will be parallel like in such a way. Then I will say here that the magnetic field lines, when it is coming in the form of south pole above and north pole down, then it is coming to being taken parallel in this way towards it. These are going to be shown around the surface of Earth in the form of magnetic field over there. These poles can be taken over to be drawn over there. So always remember that solenoid field pattern at the poles will be field lines on either side of both poles over there, and they are away from distance. As they move away, the distance increases between the field lines over there, and parallel to the surface above the Earth's surface will be drawn for them. Okay, he is saying an observer moves around the surface of Earth. All right, around the surface of Earth. Use your answer in A to explain why he observed gravitational field of Earth does not vary around the surface. So around the surface, we can say lines are very evenly spaced, and all the lines are perpendicular to surface, so it is not going to change. What I am saying, as we go around the field lines, because they never cross each other. Field lines are equally distributed, equally distant, let's say, equally distant. So the strength, and they are perpendicular lines, and they are perpendicular lines. So gravitational field of Earth does not vary. So gravitational field of Earth is not going to vary over there. Gravitational field does not vary over there. All right. Okay, now he is saying that with the reference to your answer B2, Describe how the observed magnetic field of Earth varies around the surface. Very easy. It is strongest at poles because they are originating, and we know the magnetic field is very strong near the poles over there. Strongest at poles it will be. After that, we can also say here that they are weakest near the equator because equator is in very far distant from the poles over there. So they will be weakest at equators. He has given for 3 points for this question. So at least write the 3 points for this. And they are perpendicular in case of surface of poles over there. They are perpendicular to the surface of poles over there. Remember that I am again and again saying try to write the solution as you are getting the concept, and try to little bit practice with the other papers of previous years also, and then your concept is making more strong over there. Define specific heat capacity. Specific heat capacity means the amount of energy required, the amount of energy required to raise the temperature of a body, to raise the temperature of 1 kg mass of a body, through 1 Kelvin or through 1 degree centigrade. 1 degree centigrade or 1 Kelvin. That is called specific heat capacity. If specific word is not written there, then 1 kg will not come over there. The amount of energy required to raise the temperature of a body through 1 degree centigrade, where that is called heat capacity. And when he is saying specific heat capacity, then take the 1 kg mass of some body over there. Then you can easily summarize that. Okay. Now he is saying in part number B, a block of aluminium has volume this. Very good. At temperature 0 degree centigrade, aluminium has a density of 2.7 10 raised to power 3 at 0 degree centigrade. It has density of this at 500 degrees centigrade. So temperature difference, even I am not taking in Kelvin, I can simply say here 500 minus 0, that will be 500 Kelvin equal over there. Like if I add 273 on both cases of 0 degree centigrade and 500 degrees centigrade, the result will be staying same over there. The block is heated, so the temperature increases from 0 to 500 degrees centigrade at an atmospheric pressure of 101 multiplied 10 to the power 5 Pascal, which is equal to 1 atm pressure also. And the increase in internal energy is 4.38 megajoule. Calculate the mass of the block over there. Okay, if we observe, density is given. Density at 0 degree centigrade is given. Volume at 0 degree centigrade is also given. So I can calculate the density over there. So density is equal to mass over volume, which implies that mass is equal to density multiply volume, and density is 2.7 multiply 10 raised to power 3 multiply volume is 3.26, 3.612, 3.612 multiply 10 raised to power minus 3. If we put all of these values over here, then we can just observe 10 raised to power 3, 10 raised to power minus 3 is gone, 3.612. So let's calculate little bit. 3.612 multiply 2.7 multiply 2.7 gives us 9.752. 9.752 kg is the mass for this aluminium, block of aluminium over there. He is saying show that the volume of the block at temperature 500 degrees centigrade is 3.722 multiplied 10 raised to power minus 3. So for that purpose, I will say here that volume I want to calculate. So I will use here the relation which can be named as to change the density over there. Mass I have already. So I will use here the relation that the volume is already present for both of them, and because the density is given for both of them. So I am taking here mass is staying same over there. Then I'm using the relation here, density and mass is equal to density over volume, density 1, density volume 2, and mass for staying same over there also density 2 over volume 2. So I'm equating it. Density 1 is because I need now the volume. So I'm making subject volume 2 over there. Volume 2 I'm making subject. I'm taking volume 2 in the density 1 place. Volume 2 is equal to density 2 over density 1 multiply volume 1. Just by putting all of these values, one value is 3.612, second is 2.62. Okay, so I'm using here the volume is 3 for V1 over there. I'm taking 3.612 multiply 10 raised to power minus 3. What was the volume? Yeah, that was minus 3. And for densities to be taken over there, I know they are going to cancel out their 10 raised to power 3 on both cases, 22.7 and 2.62. 10 raised to power 3, 10 raised to power 3 is going to cancel out. I'm just using 2.62 and 2.7 to be 2.7 was being taken in the form of density 2, and the density for 1 is 2.62. Let's solve it and let's check this volume we are getting or not. So 10 is for minus 3 is already available. Just check 2.7 and this value and divided by 2.62. Just introduce the fraction over here. 2.7 multiply 3.612 divided by 2.62 is equal to 3.7222, 3.722. Okay, fine. That is correct over there. 10 is for minus 3 already present. So it is 3.722 multiply 10 is to power minus 3. This is the volume for this part. Use the information in B2 part to determine the magnitude of work done. So now we need change in volume over there. And we know the work formula for gas over pressure over there or liquid over there, P delta V over there. So P, which he has given us, that was 1 atm 1.01 multiplied 10 raised to power 5. And the volumes which we will have over here, 3.722 and 3.722 and 3.612. Okay, so I am taking here, I need the change in volume 3.722 minus 3.612 multiply 10 raised to power minus 3. If I place all of these values on my calculator, what I get, let's check. 1.01 multiply 10 raised to power 5 multiply bracket start. Okay, just bracket start 3.722 minus 3.612 bracket close multiply 10 raised to power minus 3 over there, and we get this value which is equal to 11.11. So that is 11.11, and we were using to calculate the work done, which has the unit as joule over there. 11.11 joules we have obtained over there. Okay, here he is saying explain whether the work done on the block is positive or negative. So I will say here that as the volume of block increases, as we have observed there, as volume of block increases, so it is exerting the pressure outside over there. So work is done against the atmosphere. So we can say here, if work is done against the atmosphere, then we can say here that the work is negative. Work is negative. When work is done on its surrounding, then work is negative. If work is done on the system, then we take it positive over there. Use the first law of thermodynamics to determine the three significant figure values of specific heat capacity of aluminium. Explain your reasoning. Give the unit to the answer also over there. So if we just observe how much energy we were provided with, the increase in internal energy 4.38 megajoule over there. So let's check it. 4.38 multiply 10 raised to power 6, and the work done to its surrounding should be added over there as 11.11 plus 11.11. Even though this value addition will not affect too much to this value, so I will take approximately equal to the same value again, 4.38 multiply 10 raised to power 6 as my thermal energy over there. And I am using the formula Q is equal to mc delta theta energy. As I know the formula, Q is equal to mc delta theta over there. And I want to calculate the specific heat capacity of aluminium. So C is equal to Q over m delta theta. So Q is how much now? 4.38 multiplied 10 raised to power 6 divided by m mass. Mass, how much we have calculated there? That is 9.752. 9.752. 9.752 multiply change in temperature was 500 degrees centigrade. Let's introduce these values into the fraction, and let's check what is coming over there. Fraction introduced 4.38 multiplied 10 raised to power 6 divided by 9.752. 9.752 multiply 500. So the answer is 898. Okay. 898. And the unit of specific heat capacity, if we talk it, that is joule per kg per Kelvin or per degree centigrade. We can also take per Kelvin per degree centigrade over there, can be taken over there. Without further calculation, suggest with a reason how doubling the pressure in B is likely to affect the answer in B5 over there. So B5 answer, as we observe that work done is not having too much value. So I will say here work done is almost negligible over there. So we can say here, as compared with the change in its internal energy, which is having round about 9898 joule per kg per Kelvin as its value. So it will remain unchanged. It will remain unchanged. It will not be affected by 11.11. That is very minute value over there. Okay, let's move to the next question over here, where he is saying the equation of the symbol is being shown. PVA is equal to NBT. Okay. PV is equal to nRT over there, like that. Okay. And where P is the pressure, V is the volume, A is the Avogadro's number, constant, like 6.022 multiplied 10 raised to power 23, like that. And is another constant, B is another constant, and N is the number of molecules of the gas. State what is meant in the equation by the T. T is the temperature over there. So we can say that is thermo dynamic temperature. After that, identify the constant B over there. As we know, PV is equal to nRT. R is in the place of B over there. That is called general gas constant over there. That is called general gas constant over there can be taken into account. State the meaning of M and C square over there. Oh, that is easy. M is, we can say, mass of molecule of a gas. Mass of molecule of gas. And C square is, we can say that is mean squared speed of molecules are like that, are mean squared speed. Mean squared speed of molecule over there, like that, of molecule over there. Use the equations in A and B. Okay, PV is equal to nRT and PV is equal to 1 by 3 NMC square. PV is equal to N. Okay, I will have to use the same in the way over there. That is PVA is equal to NBT. PVA is equal to NBT over there. On the other end, now he is giving us the equation is PV is equal to 1 by 3 NMC square. 1 by 3 PV is equal to 1 by 3 N M into C square, like that. Then I will say here that how we can take it in the form of this form to show the values over there, how kinetic energy can be taken. Use this expression of AB, mean kinetic energy of the molecule. We want to calculate that. So as we know, the kinetic energy from this equation over there, PV is the work done, and 1 by 3 NMC square, we know that it should be taken as 1 by 2 MV square over there can be taken. So PV is equal to nRT will be taken. Then I will say here kinetic energy is going to be equal 1 by 2 M with root mean squared speed velocities of 1 by 2 mv square over there. And on the basis of this, if I compare both of these equations, then PV is gone, PV is gone, and A is coming down of number of molecules over here. And that is equal to Nm over like this over there. And B is general gas constant in that case. And NMC square is going to be taken. Just I am multiplying here with 2 above, multiplying also and dividing also. And the dividing is 1 by 2 MC square, 1 by 2 M C square over there. That is also being multiplying by 1 by 3, and that is 2. And 2 by 3, 1 by 2 MC square. And this is kinetic energy, by the way. And on the other end, if I am taking this for NBT case, then I will say here that it is going to be taken as BT down, so that NA can be making the fraction over there. Then I will say here that it is BT over 2 with Avogadro's number A over there. So 3 is coming up and 2 is coming down. So 2 is cancelled over there, and this 3 is coming up. So kinetic energy 1 by 2 mv square can be given as 1 by 2 mv square is equal to mc square, by the way, being taken equal to BT with 3 value over 2A. So it is 3BT over 2A is my kinetic energy for this expression over there. Okay. In the next part, he is saying that sketch the graph variation of T with root mean squared speed of the molecule, and this axis temperature is there and root mean squared is there. As we know, temperature and kinetic energy are directly proportional to each other. So there is a smooth curve with the positive gradient over there. If I say here that it is in this form with the positive gradient, and if I take a gradient at this point, that is to be going to pass through this center of origin over there, and positively decreasing, it will be positively decreasing gradient over there. So not to worry about its graphical representation over here. I will suggest you that this is a curve of square graph, as you have studied in mathematics, that the x square is having curve like this. Okay, this is the graph like this, and if I say it is more flat like this, then it is a decreasing positively gradient will be taken into that case, which is going to pass through the origin over there. Okay, let's move the question number 5 over there. What is he saying over here? What is meant by simple harmonic motion? Remember that simple harmonic motion is the chapter of oscillations, level ATIONS, oscillations, and he is talking that what is simple harmonic motion. Remember that the motion in which acceleration is directly proportional to negative of displacement, the motion in which we can say, I'm just writing the characteristics of simple harmonic motion over there. And I can say here acceleration is acceleration and displacement x are always in opposite direction, always in opposite direction, opposite direction over there. I can also say here that acceleration is always directed inward. Acceleration is always directed inward. These are three characteristics of simple harmonic motion. After that, he is saying here, a bulk is given. Okay, calculate the period of the oscillation over there. And okay, this is the formula which is given in the form of V is equal to 0.56 cos 16t. If I take the formula, V is equal to V naught cos omega t. So from here, he is saying calculate the period of oscillation. Period of oscillation, it means I will have to take this 16 and omega equal. Then I will say here omega is equal to 16. Omega is equal to 2 pi over t. I also use this relation in circular motion over there. I need t over there. So t is equal to 2 pi over 16 there. If I simplify this by using calculator, let's check what is coming over there. Fraction introduced, 2 pi divided by 16 there equals to this, equals to 0.39. So it is 0.39 seconds is the period of this value. Determine the amplitude of oscillation. So you remember the formula over there, V is equal to X naught omega there. So X naught is amplitude which is being taken over there. So he is saying amplitude to calculate. So take X naught is equal to V over omega. And we know that the V which is given over there, that is 0.56 as its maximum speed of V naught over there. So I'm taking here V naught is equal to X naught over there. So V naught is being taken as 0.56 there. And I have made X naught as a subject. Okay, omega is down over there. Now in place of omega, I'm simply saying here, just use the relation of pi by 16 over there. What was omega value over there? Omega was equal to 16. So just use this value 16 over here. And it is 0.56 divided by 16. 0.56 divided by 1. 0.56 divided by 1 6 equals to 7 over 200, which is equal to 0.035. 0.035. This is the amplitude of this relation. Using to determine the equation of our V in terms of displacement x of the block where V is in meter per second and X is in meters over there. All right, if I make here V as a subject, 0.56 cos omega t, now I want to calculate this relation over there. And if I make V as a subject, then I will say here that in the original relation, when I am taking V is equal to X naught omega like that, then I am saying it is X naught into we can say there that it should be V is equal to X naught omega. So X naught should not be taken. It will be omega into X naught square minus X square. This is the basic formula when I need instantaneous velocity over there. Then omega was equal to 16 there. 16 under root X naught, you have this value 0.035, 0.035, which can be taken in the form of square over there. If you want to take it square, you can. Minus X square will be taken in the both format over there. Okay, this was your instantaneous velocity in the case of Earth's motion over there. Okay, now he is saying sketch the variation of V with X over there. So remember that I will draw a closed loop over there around the origin. Then I will say I am drawing like this. I am drawing like this. A closed loop around the origin I am taking into account for drawing the graph sketch over there. I'm taking this like in this form. So I will say loop crosses be equal to 0 over there, and that loop is going to cross with 0 and have maximum value at X at 3.5 over there. So it means I have done something wrong over there. Loop should be taken like this form. Okay. It should get its maximum value at this point and minus 3.5. It should get its maximum value at this point. So I am removing it. Please wait a second. Don't worry about it. I have done something wrong with it. Let's check that the loop is going to surround the closed loop surrounding the motion over there. It is having its value 3.5. It should have this value over there. Then it should pass through here. And then it should take its value here. And then it should take to fall like this. So this is the loop which is going to be taken over there. In the same way, it should pass surrounding the origin like in this form and like in this form over there. All right. Okay, this was our question number 5. In the next video, we will be going to do from question number 6 to question number 10 also, or 11 also. So not to worry, kindly subscribe my channel and wait for the next video over there. Thank you so much for today. Allah Hafiz.